Z-score of an observation tells us how many standard deviations the observation is from the mean. The z-score of an observation x is calculated as z is equal to x minus mean over standard deviation. Z-scores can be positive, negative, or zero. If z-score is positive, the observation is above the mean. The more positive a z-score is, the more that observation lies above the mean. If z-score is negative, the observation is below the mean. The more negative a z-score is, the more that observation lies below the mean. If z-score is 0, the observation is equal to the mean. Example, find z-score of 55 if mean is 52 and standard deviation is 4, so z is equal to x minus nu over sigma. And 55 is the x in this case because that's the value whose z-score we want. So 55 minus the mean, which is 52, divided by the standard deviation, which is 4. So that is actually 0.75, not 0.075. Example, points A, B, C, D have z-scores given below. Z of A is 3, Z of B is -1, Z of C is -2, Z of D is 1.5. Which of these points is the greatest distance above the mean? So the point which has the most positive z-score will be the greatest distance above the mean. And A has a z-score of 3, which is the most positive among these. So A is the greatest distance above the mean, while C has a z-score which is the most negative. So C lies the greatest distance below the mean. Example, the mean ACT math score in a certain year was 22.6 and standard deviation 3.5. The mean SAT math score in the same year was 550, standard deviation 51.6. Which score is relatively better, 33 on ACT math or 700 on SAT math? Well, to compare these kind of scores where it's a different scale, we find the z-scores of both, and whichever has the higher z-score is the better score. So for the 33 ACT in math, we do 33 minus the ACT mean divided by the ACT standard deviation. So the ACT mean was 22.6 and the ACT standard deviation was 3.5. So 33 minus 22.6 over 3.5, that gives 2.97. Whereas z-score for the 700 SAT will be 700 minus the mean of SAT, which was 550, divided by the standard deviation of SAT, which was 51.6. That's 2.91. So since the 2.97 value is bigger than 2.91, so the 33 ACT is better than 700 SAT. Example, a college will accept only those students whose ACT is at least 2 standard deviations above the mean. If the mean in a certain year was 22 and the standard deviation was 3.5, what's the minimum ACT score needed to get admitted? Now, remember that z-score is the quantity that tells us how many standard deviations we are from the mean. So in this case, we are talking about 2 standard deviations above the mean, so z will be positive 2. If we are below the mean, then z is negative accordingly, depending on how many standard deviations we are below the mean. In this case, we are above, so z is 2 for the 2 standard deviations. So we'll calculate the score corresponding to 2 standard deviations, and that means we'll need at least that much score. So mean is 22, standard deviation 3.5, so we use our formula z is equal to x minus nu over sigma. So z is 2 in this case, x has to be calculated, minus the mean, which is 22, divided by standard deviation. So to solve this for x, we multiply both sides by 3.5, and that gives you a 7 on the left side. 7 is obtained when 3.5 is multiplied by 2. So 7 equals x minus 22, and we add 22 on both sides. So x is 29. So the minimum ACT score needed is 29. Example, the mean height of women in a city is 62.6, standard deviation 2.5. Find the heights that are between 1.5 and 3 z-scores. So in this case, we are given two z-scores. One is 1.5, the other is 3. So we will find heights corresponding to both of these z-scores, again by the formula, z is equal to x minus nu over sigma. So the first z-score is 1.5, so you substitute 1.5 for z, and we're calling x subscript 1.5 as the corresponding height, minus the mean. Mean was given to be 62.6, standard deviation 2.5, so minus 62.6 divided by 2.5, multiply both sides by 2.5, and then add 62.6, so we end up getting 66.35. That's the height corresponding to a z-score of 1.5, and then we need the height corresponding to a z-score of 3. Remember, second z-score was 3. So 3 is equal to x3 minus 62.6 over 2.5. Again, 62.6 was the mean, 2.5 was the standard deviation. Multiply 2.5 on both sides and add 62.6. We get 70.1. So the heights that are between 1.5 and 3 z-scores are 66.35 and 70.1. So everything between 66.35 and 70.1. Example, mean lengths of balls is 13 centimeter. Let's say mean length of balls is 13 centimeters, standard deviation 2 centimeter. You want to discard all balls that are more than 3 standard deviations from the mean. Which lengths will be discarded? Now, 3 standard deviations from the mean could be on either side of the mean. So we will find the lengths for corresponding to z is equal to -3 and z is equal to 3. Because if you are below the mean 3 standard deviations, then z is -3. And if you are above the mean 3 standard deviations, then z is equal to +3. So formula is once again z is equal to x minus mean over standard deviation. And when z is -3, you'll have x subscript -3 minus the mean, which is 13, divided by standard deviation, which is 2. So multiply 2 on both sides, get -6 here, and when we add 13 on both sides, we get x as 7. Similarly, we repeat it by putting z is equal to 3. 3 is equal to x minus 13 over 2. Multiply by 2 and add 13. We get x equals 19. So we discard lengths that are less than 7 or greater than 19, because we are to discard lengths that are more than 3 standard deviations from the mean. Now, if we are between 7 and 19, we are within 3 standard deviations, and if we are less than 7 or greater than 19, then we are more than 3 standard deviations away. At 7 and at 19, we are exactly 3 standard deviations. So to discard, you have to be less than 7 or greater than 19.